Thanks so much. My name's Tony Martin. I am doing some contract work for Delphi, and myself, Dave, a few others, Rick Esquilambri.
Oh, he's the one
Uh,
who's doing
yeah, yeah. Several others have been kind of been listed, and we're doing some. Well, in this case, a Tech Tip Thursday on a webinar, and I'll be doing this subject for HDA Truck Pride in Des Moines, Iowa next week. This time next, as a matter of fact, Thursday of next week.
it.
So yeah. Anyway, so this is today's topic: J1939 Controller Area Network Diagnostics. J1939 has been around for a good long time, but we're going to talk a little bit today about practical approaches to diagnosing problems with J1939. Just a little bit about me. I started out in as a heavy duty mechanic apprentice, heavy duty equipment mechanic apprentice in 1984 in Brandon, Manitoba, in Canada. And I went to work. My first job was working for an International Harvester dealer back when International Harvester was still a thing. They used to be a mighty corporation, and then they became less than mighty over time. But they had a truck line that I was interested in learning about. There was an ag shop and a truck shop, and I worked in the truck shop. Um, at that time, there was nothing coming in the door that had electronic engine control, let alone networking on the vehicle. So this is all just in its nascent form at that particular time. And I got into the trade just as the electronic diesels were coming into play. Um, After I finished my apprenticeship, I went on to run a mobile repair of my own and used to service an area about 60-mile radius from the city that I lived in there in Brandon. Eventually, through a different long set of circumstances, wound up immigrating to the United States legally, by the way. I'll just say that. But anyway, just saying. Anyway, let's see, went to work in the oil field, learned about gas turbine technology, and used to fly around in helicopters going to offshore oil platforms, stuff like that. Kind of got away a little bit from the mobile equipment. Eventually went back to school, got an education degree, and then started teaching. And my first teaching job was in Barrow, Alaska at Illisaga College. For those of you who don't know where Barrow is, it's just go right to the very top of Alaska, facing the Arctic Ocean. And that's where I taught for 5 years. I taught automotive, I taught some welding, I taught heavy duty mechanics there. And then that's in 2001 turned into a job at University of Alaska Southeast in Juneau. And after I was done there, 12 years later, I went back to work in private industry as a trainer in the mobile equipment maintenance department at a corporate gold mine outside of Fairbanks. And so that job, that was a change of pace, different product line, a lot bigger iron, same principles though. They still work on the same principles as everything else. And but it was a good experience. It was basically kind of reinventing myself there for a stretch. And today I'm freelancing. So I'm doing consulting and training and writing and things and kind of running my own business. And this is part of what I do now for Delphi. So I'm really happy that I was able to reestablish all the contacts that I had from years ago. When I went into the mining industry, I kind of left a lot of stuff behind, and fortunately, a lot of it stayed. So really glad about that. But anyway, yeah. So thanks so much for coming, people. And today, our agenda, we're talking about J1939. What exactly is it? You've heard the term probably a bunch of times, but what exactly does that encompass? We're going to talk about how CAN networks, controller area networks, relate to J1939, how that's part of that protocol. Then the CAN system design, serial data gateway modules, and then we just go straight into, hey, what could go wrong? What could go wrong with these things, and some resources for diagnosis, diagnostic steps, some rules of the road, if you will. a little bit about DSOs, and we'll touch on repair tips. We've only got an hour, so we're just hitting the highlights here is what we're doing. But starting us off, what is J1939? And basically, Dave and I were talking about this yesterday. It's kind of like global OBD2 for heavy duty equipment, is what it is. Because on the one hand, it's using hardware that pretty much everybody uses, but it's using a language that everybody can communicate with. So across brands, across different kinds of machines, and so on. So basically, it's a focus on heavy duty vehicles. But if your vehicle, if the machine that you're working on has a J1939 network, then it's talking the same language as any other J1939 machine. And this goes for lots of different kinds of machines. Started out with buses, really, and over the road trucks, but as you can see, kind of encompasses just about all heavy equipment that you can think of, including stationary stuff like power generation and oil refineries. It's used extensively in mills, chemical plants, on and on and on. J1939 is a common protocol being used in all of these different areas. Now, the one that we're focused on today is the trucks, and we'll mix some buses in there too, kind of thing. But on-road trucks is kind of where our major focus is today. And but again, to be clear, the same concepts, the same technology is basically used in all of these machines that we kind of associate with the heavy duty realm, if you will. A little bit of history on where it all came from. Okay. So 1994 was when J1939 was first conceptually proposed, and the standards were released at that time, the initial standards. Up until that time, any any on-road truck that had electronic controls, which would have been a lot of them by that time, for certainly for engine controls, everybody had their own diagnostic connector. Does this sound familiar? Okay. And what do you know? Okay. Eventually it became standardized. The whole notion of having everybody with a different language, everybody with a different diagnostic connector, and so on and so forth. I know you automotive guys out there know this is like, weekend at Bernie's, right? Been there, done that. Anyway, so 2000, there was a top level document that was published, which basically defined what J1939 would look like, and it formalized the idea of using a controller area network as it's what's called a physical layer. So it didn't just discuss the language. J1939 is primarily the language, but it also formalized CAN as what was going to be the physical layer. It was going to be used on a CAN network is what it was going to do. And there's really good reasons, engineering reasons to do that. More on that in just a minute. So there were standards that had been in place leading up to when J1939 was established. They were known as J1708 and J1587. Basically, J1939 was replaced those, okay, in 2001. And there was also a conversion that went with the data link connector. So for the period from 1996 through 2001, there was a standardized 6-pin Deutsch connector that was used for the data link connector. And then when J1939 came along, there was a 9-pin connector that replaced the 6-pin Deutsch. And then by the time in my sense is, as I read into this, my sense is that everybody was really happy when J1939 came along because there were some severe limitations on the particularly the bandwidth for the old J1708 standard. So yeah, up to 1995, everybody used their own diagnostic connectors. 1996, sound familiar? The 6-pin Deutsch connector was made standard. In 2001, 6-pin to 9-pin Deutsch. And then 2014 was another milestone. We'll talk about that in just a moment. Okay. If this looks familiar, okay, looks like CAN, controller area network. Well, okay, if you're using J1939, you're going to see on the oscilloscope, you're going to see patterns very similar to this, is what you're going to see. So anything you know about controller area networks is going to help you when it comes time to dealing with J1939, because again, the physical layer is effectively the same thing. All right. Now, this looks familiar to most people in the audience, I'm thinking. J1962 data link connector, which was established 1996, right? Model year in automotive. There's a correlation between the J1962 data link and the Deutsch connector, the 9-pin Deutsch connector, which I'm going to show you here in a moment. 16 pins, they all have the pinouts have all been assigned, right? There's assignments for these pinouts as described in the slide that you were looking at right now. So here's the Deutsch 9-pin DLC. And you guys will notice that while all the terminals are the same size, the terminals themselves are the same size, the sheath or wrap around the terminals is different diameters. And that's important because there's two different designs of this Deutsch connector, and they're not thoroughly, let's say this one here is backwards compatible. The one it replaced is not. It's pin F. And in the case of the older connector, the pin F had a larger sheath on it, kind of thing. And there was a reason that was replaced. There was a big upgrade that took place for J1939 in 2014, and that involved going from 250 kilobits per second to 500 kilobits per second. So there was a big upgrade in the capabilities and bandwidth for J1939 at that point. But you didn't want people with the old service tools, the electronic, in the heavy duty world, scan tools are known as electronic service tools. So you didn't want somebody with a dated service tool hooking into the new network. You did not want that. So consequently, they made it so the old pin F was much larger and would not fit into the new Deutsch connector as of 2014. Now, we talked about the correlation between the J1962 and the J1939 DLCs. And these are basically the pins they have in common. So A would be a ground here. Pins 4 and 5 here are grounds as well. You've got first of all, you've got pin 16, right, is battery power. So that correlates with pin B on the Deutsch 9-pin. Then you have your CAN high connection, which is C here, and that correlates with pin 6. And then the D pin is the same as CAN low, which is pin 14. So there's a adapter I'm going to show you in just a moment. Well, I think I already showed you a picture of it, right? No, didn't yet. Yeah, there it is. Okay. That's an adapter that goes from the J1962 16-pin, as we affectionately know as the OBD2 data link connector, adapts that to the Deutsch 9-pin. Okay. Now, this is where it describes the difference between the black connector and the green connector. So this is the prior connector that was good up until, let's see, it was good from 2001 through 2014 or so. And you'll notice that pin F has a much larger sheath on it than pin F on the green connector. So This green connector can be plugged into the old network. This connector, the black one, cannot be plugged into the new network. And pretty important stuff, actually. I'm told that plugging if it was possible to plug an old service tool into the new network, could create some damage, havoc at the least. Over here on this side, you guys can see that pin C and D are CAN high and CAN low, which we showed you in a previous slide. Pin F and pin G were dedicated to the old network that it was replacing. So when J1939 came along, they didn't want to make it so J1708 was not accessible. So basically, those two pins remained on that connector and basically access J1708, because there was lots of manufacturers that had J1939 simultaneously with J1708 on the machine. And it took a little while for this to go away completely, but that's what those two pins were dedicated to, was J1708. Down here, you can see type 1, the type 1, the black connector. That was the old CAN that was good to 250K. The new CAN, good to 500K. Something you should know about the old J1708 was the bandwidth was only 9.6 kilobytes per second, kilobits per second. So let's just say that the engineers were good and happy when the J1939 came along, because they were severely limited with the old standard J1708. So how's your short-term memory doing? This would be a black connector. You guys can see this little key here on middle pin A, and it points towards pin F. And you can see this is a large pin. This would not fit into a 2014 or newer vehicle. This is only good for the 2001 through 2014s and the black connector that was associated with it. And as I mentioned previously, the black 9-pin connector, the J1939 network at that time, was designed for 250 kilobits per second. This is another J1939 connector that you may quite possibly will deal with, but it's not located in the cab. It's going to be under the hood in the engine compartment. And it would be for doing reflashes. You connect directly to the backbone of the network, particularly the powertrain and emissions side. And so it's possible that there's certain functions that you might wind up accessing using this 3-pin connector that's found in the engine wiring harness. So that's the Deutsch 1939 3-pin. That would be, again, not located in the cabin, but in the engine compartment. Anyway, so it begs the question now, you guys, for anybody who's been following and looking at, the way that the networks have been configured and built in recent years, there's multiple networks that are being utilized. And that goes for cars. It all started with cars. Heavy duty is typically 5 years behind whatever's happening, or more, right? Whatever's happening in the automotive world. But it begs the question, right? Why do we have so many networks on the vehicle? And in the case of heavy duty, like J1939, you're asking more and more from the network every model year. Every model year that comes along, there's more stuff that has to be accomplished. And so consequently, the engineers look at it and they say, we've got all this stuff that doesn't require a high-speed network that still needs to be networked, but we don't really want it on J1939 because it's going to start creating clutter. There's enough other high-priority stuff going on there that we don't need, for instance, driver's window up, down, stuff like that. We don't necessarily have to have it on any kind of a high-speed network. So you create other networks. And then you create gateway modules that are going to talk the language of each network and be a translator, if you will, between J1939 and these other lower speed or maybe even higher speed networks. You got something called MOST now. Media oriented is what it is. Most media oriented. Dave, help me out. Media oriented standard transmission. Is that what that stands for? I'm trying to remember.
Yeah, media oriented. Uh, I think you're correct. But there's two physical layers. Like they use that term a lot with CAN, physical layer. That means the wiring or the way
Yep.
they can transmit information. The Euro cars use an optical, fiber optic, and GM uses a hard wire, to it like regular copper wiring. So
Okay.
yeah, media oriented system transport. I believe that you're correct in that.
Uh, okay. But that's a lot wider bandwidth,
Yeah.
like big time, right? And so a lot of stuff that isn't okay. So J1939 now is pretty much related to powertrain and emissions. And my understanding is this, despite the fact that X years ago, quite a long time ago, everybody was saying it was going to be replaced by something else with more bandwidth and so on and so forth. We're kind of still chugging along with it, and you might call it the global OBD2, right? Or of the heavy duty world, just because again, it's a ubiquitous language, right? Meaning everybody uses it. And we've narrowed the responsibilities of it down to powertrain and emissions kind of thing. But anyhow, nowadays, anymore, as you know, we've got multiple, and trust me, this is not just for on-road trucks, mining equipment, 793F Caterpillar, 250-ton uh, mined truck, right? And the sucker's got at least three networks on board that I recall. And two of them are CAN as well. So it's not just happening in automotive, it's happening across the board with pretty much every mobile machine and stationary stuff that you can think of. So so a little bit of something you should be familiar with is the whole notion of network topology. And the reason this is important for the repair technician to know something about is because if you're going to be doing diagnostics on one of these networks, well, first of all, you got to understand there's going to be multiple networks. You're going to have to narrow down which network you're even dealing with in the first place. And you're going to have an idea of how this stuff is all connected together, including your data link connector, your DLC. And how does that actually connect to the networks? Okay, in this particular case, it goes to a gateway module, which is full up with termination resistors in this case. But it's connected to one, two, three, four, five, six different networks. And if you're trying to narrow down a problem with, say, a body control module here, you're going to want to know what network it's on, what other modules are on that network in order for you, and how they're wired together in order to be able to do your diagnostics. So the topology thing, the terms, probably less important. The point is understanding how all this stuff is connected, is hardwired together kind of thing in order to, be able to diagnose effectively. Baud rate. So we just talked about this, the whole notion of low speed, medium speed, and going up into things like FlexRay and Ethernet and most. Okay, just like David was just saying, there's an optical and there's an electrical most here. There's FireWire. So here's another one. And you would have thought that J1939 would have been replaced by one of those ages ago. I think it has something to do with the federal government, and we all know how the federal government moves. So we've we've had to adapt. But as you can see, there's technology out there that can take us a whole lot further and faster than where we're at right now. But regardless, J1939 lives on. Twisted pair. Understanding what you need to understand here is dealing with electromagnetic interference and also creating electromagnetic interference. So when you have a twisted pair like this, what you're basically doing is resisting the influence of external electromagnetic interference on your network. And you're also limiting the amount of influence your network has on other networks and on other devices. So it's kind of like a private party of sorts, right? It's kind of like limiting your guest list, and you're making sure that what you're saying and doing is not necessarily going to um, offend or, cause other problems, influence other conversations. We're trying to keep this to ourselves. So that's what Twisted Pair is all about. Getting this right when you're doing repairs on the system is critical. More on that in just a minute. Take a look at termination resistors. And this is a slide that I borrowed from Dave, which I think sums it up really well. Why are the termination resistors so important to the network? Well, first of all, they cannot function without them. They could function without one, but if you lose both, everything's over with. The termination resistors are that important. And for those of you who remember the Citizens Band days and all of that stuff, okay, what you're doing with the termination resistor is kind of creating a bit of a dampener in the system. A dampener and also a means of helping stabilize everything. Okay. The whole notion of signal reflection and ringing in the system. Whenever you're putting up, it's kind of like, you turn on the tap on your say in your bathroom. Okay. You turn on the cold tap and then you shut it off suddenly. And what do you hear? You kind of hear a thump, right? Okay. That's the momentum of the water kind of hitting the end of the tap and then kind of shuddering through the rest of the system. So the whole plumbing system kind of feels it. Well, that's kind of what goes on when you turn your ones and zeros off and on your network. Okay, is you got all this electrical momentum, and you got to deal with that somehow because otherwise you're going to have reflected and reflected signals and ringing that's going on, and it's effectively going to try. It's going to influence the accuracy of your communication. So to prevent that, termination resistors are located on each end of the backbone. Now, another thing I like about this slide is that job two, the throttle return spring is a really good concept. So when you go from a zero, which is let's say CAN high, we go from a 2.5 volt at rest, suddenly turn it up to 3.5 volts and then turn it back off again. Well, there's a lot of residual energy that it doesn't just turn off just like that. It basically kind of hunkers down slowly. And if it wasn't for the termination resistor that's at the end of that backbone, you would not have the sharp turn off and then go back to 2.5 volts just like that. It's going to have a tendency to kind of hang around a little bit and kind of slowly dissipate is what it'll do. So the termination resistors are absolutely critical in not just the operation of the system, the network, but they're also absolutely critical for diagnostics. Very handy. More on that in just a minute. So here you have a very simple J1939 network. You can see your engine control module here, okay, is acting as a gateway of sorts because there's another network attached to it up here, okay? Other than that, all of these other modules are all connected to CAN high and CAN low. This is called the backbone. So the horizontal lines are known as the backbone, and you can see the backbone has termination resistors at each end. The branches or stubs are these little lines that come off of it, kind of like I think, Dave, you used a analogy of a rail line and then a branch line coming off the rail line or something
Yeah,
like that.
yeah, the main line. Yeah, the main line versus the short lines.
Right. So
The short
this,
lines take the cars with different locomotives up to the places where you have the pellets or feed for the livestock, whatever, the
you're
granaries.
you're talking Indiana language there. That's good. If it
Yeah.
was here, it'd be gold ore or something like that, right? But
Yeah, yeah.
so we're betraying our regional influences here. But
Right, right.
but you can see why it's important that you understand that a certain module has a branch leading it into the backbone and so on. That's going to have everything to do with your diagnostics if there's a problem on the network. So having an idea of how all this stuff is laid out, your topography, if you will, right, is critical on, as far as diagnostics is concerned. Also understanding where you have opportunities to disconnect stuff for diagnostics. And that's where these splice connectors come into play. So you need to have an idea where those are located as well, because you can see, for instance, on this two-wire bus splice connector, you can disconnect certain modules just one at a time and go looking for problems that way. There may be some special tools that are involved in installing, reinstalling, or disconnecting these kind of thing. But having an understanding of where those exist on the network and knowing how to use them strategically to narrow down problems is very, very important. So, diagnostic gotta haves. Gotta have a breakout box. There's numerous different types out there. I think, Dave, you use the Power Probe one. Is that correct?
Yeah, yeah, I just got it, and I had the one before the one in the picture. That's the
Okay.
OB. That's the oh gosh,
Line spine.
yeah, well, yeah, it was made by OTC, I believe. It looks like AES Waves got their co-branding
Yep.
on it. It's got a little digital thing and a few LEDs. The Power Probe has all LEDs on every pin except the grounds, and then you can hit a little button and change which bus circuit that you're looking at the voltage, and it's
Mhm.
pretty accurate. I've noticed, it's not far
Really?
behind a meter, a regular meter, because it is a meter. Of course, you're going to get into scopes in a little bit, but yeah, I was impressed with it. It's the fact it's on a new Toyota in my driveway right now.
Good. Well, this is going to save you just a whole bunch of trouble.
Yeah, yeah, trust
Like
me.
a pile of trouble. If you're thinking about the idea of back probing a data link connector and stuff like that, yeah, have at it. This is just going to make your life so much easier. And so find a good one. There's a number of good ones that are out there. This is the adapter. I alluded to this earlier. This is the adapter that's going to take your 16 pin uh, OBD2 connector on this to the Deutsch 9 pin, and then be able to access the stuff on a J1939 network. So that's an adapter that you can purchase. I got mine from Autel. And then I think we already talked about the business of pin F here. You see the little key right here on pin A. It points towards pin F. This is the small one, and this is the one that's going to be backwards compatible. It'll take you all the way back to 2001. But primarily for the 2014 and newer G1939 networks that are at 500 kilobits per second. Get a good digital multimeter. I don't know if you have to spend a whole bunch of money, but you should get a good one, the best you can afford. And you can see here that we're measuring between or across pins 6 and 14, and we're seeing 60 ohms. So we've got 220 ohm termination resistors that are on the network. You take those and put them in parallel, and the resistance you ought to measure or should be seeing on the digital multimeter is going to be, I'm told, plus or minus 10% is a good number. Does that sound right? So this was pretty close to 60, but you could accept 10% on either side of this as being good. Having the banana plug jacks here for your leads is really good. And being able to attach, back probes and things and such gives you a lot of flexibility when when your leads are the banana plugs at both ends. Okay. Now, rule number one, you've got an issue that's been reported to you that could be network related on a machine. The first step is to gather as much information as possible. And this is just basically doing your research, is what it is, okay? But some things never change. And this should be the first steps with any kind of problem that you approach, right? Any problem you're tasked with. you've got an issue, and these are the first steps that I think General Motors might come up with this initially, right? The Everybody does it now, right? Verify the customer concern. Make sure that you understand what the problem is first, and that you can see what they're concerned about. And if you can't see what they're concerned about, you're going to have a heck of a time. Yeah, you're you won't know if you got it fixed, right? So verifying the customer concern is absolutely critical. And then a basic visual inspection. How many problems do we find where a simple visual inspection was the last step we had to make, and we got it fixed? Okay. Um, Sometimes some really simple things that everybody else is overlooking is picked up on a visual inspection, and you don't even bust out your toolbox. You know what I mean? So taking some time to do a little bit of this and getting a bit of an idea of what the lay of the land is on this machine. Then take your scanner and retrieve as much information as possible. You could be talking about U codes here, right? I've heard U was basically an acronym or a short for unidentified. Dave, you had another one, didn't you? What does the U
U
stand for?
UART, Universal Asynchronous Receive and Transmit. It was the
Really?
first data bus used by GM. I think it dates back to my 36 years ago,
That's
leaving
where the
Hobbs
U came from
Electric.
in U
Yeah,
codes?
going to Delco Electronics. Yeah, they called it UART, and it was GM
Yeah.
because,
Okay.
yeah,
That's new for me. I did not know
yep,
that.
yep. And so
Okay.
they had to call it something. So the U
I
and
guess so.
UART.
Okay, because I've heard of different renditions, but that sounds credible to me.
And that
So,
the yeah, that the other one may be correct. Who knows?
okay, well, we'll let GM take the credit. Anyway, um, okay, this last one here, reviewing the vehicle service history. Okay, when did this problem start? And this truck was in the hands of a different technician like a day ago or two, and now it's got this problem. Or you've got something else that was done to the machine that somehow or another now is influencing the operation of the network of the J1939 network. So having a an overview or being able to review the service history, any problem that you're dealing with, this is going to be important to do. So these are just simple. You're going to do this. It doesn't matter if it's J1939. It's going to be any problem you're faced with. This is stuff that you ought to be doing. Okay. But rule number two. So you're narrowing it down. You're figuring you might have a problem with the network. Well, you need to know your network. You need more information. And that starts with a comprehensive wiring diagram. So this is in component locations. So understanding the wiring diagram and understanding where the components are located is going to have everything to do with your diagnostic strategy. Because let's say that you're thinking to yourself, okay, I'd like to get after this splice pack here or a connector here, but I'm going to have to take apart the truck to do it. However, we have one that's over here that could yield some information that I can get to in like 2 minutes. You're probably going to go in that direction, right? And see what you turn up with the stuff that's more easily accessible. But you won't know about any of that stuff unless you have a comprehensive wiring diagram. If you take a look at this one, it even gives you the turns, in this case, 9 turns per foot in that twisted pair. So it's giving you specifications on the number of twists that are supposed to be in the twisted pair and such, right? But and also the location of the termination resistors. So this one's located in the engine control module. Whatever module this one is here, this is where the other one's located for this particular backbone. Okay. So these are questions that you're going to be answering or trying to answer. What network is the module located in? Could be one of how many? Just depends, right? But 3 networks on board any off-road or pardon me, on-road truck is probably not unusual anymore. So you need to know where that module is located and what other modules are on that same network. How are the modules connected? Where are the termination resistors located or terminating resistors? And are there any splice packs that we can get at that can possibly help us like take out one particular module and see how that affects what's going on? And another question you need to answer is, where are gateway modules located? Because that's going to have everything to do with your diagnostics as well. And I'll show you here what I'm talking about. Okay, so here is a gateway module. Okay, on the one side, we have the control area network and the twisted pair. Here's our backbone running through here, terminating resistors on both ends. Here's our branch lines, and here's a CAN ECU here, electronic control unit. Here's another one. And so we've got four modules that are on the CAN, but through this gateway, we can also communicate with these local internet or interconnect network modules that are on a different low speed LIN bus and share information back and forth through this gateway. So having an idea of where the gateways or knowing where the gateways are located is super important, and their function as well. Okay, because there's also the secure gateway module that can cause some grief for you potentially as a diagnostician. What are the things that can go wrong with the bus and cause faults? Okay, so this isn't downing the bus. This is just creating diagnostic trouble codes, faults, hasn't disabled the machine. Okay. Either data line could be shorted to ground, not both, but one could be shorted to ground and would not disable the network. But you're going to get DTCs and bus communication faults. If you have an open in either data line, it could cause these problems. And you can get away with one open or missing terminating resistor. Okay, so that won't disable the machine, but you are going to see problems. Okay. Now, the stuff that can cause no communication on the data bus includes if you have either data line that gets shorted to battery power, it's going to bring the bus down completely. If you take one data line and short it to the other one, same thing. And then finally, if you have failure of both the terminating resistors, that will definitely bring communication to a halt on the network. So it's kind of like a level 1, level 2 thing. This is what it is. But these are physical problems with the network, and we're trying to figure out, okay, what are good strategies to help us narrow down those problems.
Bless you. Again.
Hello. So yeah, here we have, this is a tool you make for yourself, just fuse jumper lead. And what you're going to use that for is disconnect the power off this battery. This is just an old Dodge Grand Caravan is what it is, but same idea. Disconnect both the battery leads from the battery and use this basically to drain any residual energy to ground. If you take a look here, I've got this fuse jumper lead in place. I've got both the battery negative and the battery positive cables removed from the battery. And I've got the fuse jumper lead in here. And watch what happens to the meter. Right now, across those two cables, when they're shorted together effectively, we've got 0 volts of potential. But if I take it's probably been on there for about 10 minutes. If I remove the fuse jumper lead, watch what happens. It's recovering. I mean, it's not a lot of voltage, okay, but it's just telling you there's still energy there. And it's going to take a little while, even with that jumper lead, to completely dissipate that energy that you're seeing on the voltmeter. So basically leave your jumper lead in place while you're doing this test. Okay. And again, this is just connecting a digital multimeter in the resistance range and connecting across pins 6 and 14. And you can see that we can see both our termination resistors are intact. This is a known good car, though. Keep that in mind, of course. Okay, so here we are back to our basic J1939 network. And right now, if we connect our digital multimeter to pin C and D, which is the equivalent of pin 6 and pin 14 on our breakout box, if everything's good, we should be seeing 60 ohms. You've got 120 ohms here for this terminating resistor. You've got 120 ohms. These are in parallel. So this would be the total resistance of the 220 ohm resistors in parallel. What if your data link connector doesn't go directly to the backbone? What if there's a gateway module here, which then in turn is connected to these networks? How's that going to affect your troubleshooting? Well, you're not going to be checking your terminating resistors here in these networks through the data link connector. You're going to have to back probe like here and here or here and here or something. You're going to have to be on the other side of the gateway module to do these same tests. So you can see why it's that important that you have that comprehensive wiring diagram so you know if that gateway module is going to impact your diagnostic procedures, right? All right, so here we have a gateway module that's been installed on that same data bus. Here's our J1939 data link connector. We're measuring ohms again. We're measuring resistance. And we've got a 60 ohm terminating resistor here in the gateway module. The other terminating resistor is in the scan tool if you connect to this. Okay, so there's still going to be two on that section, right? Data link connector and the gateway module. You're still going to have two terminating resistors, but the other one here is going to be for this section is going to be in the scan tool. Now you got your, so what are you going to see on the meter? You're going to see 60 ohms. This could be misleading if you're thinking that you're actually measuring all of this stuff and you're not. So that's why you need to understand where if there's a gateway module involved, and if there is, you're going to have to be back probing on the other side of this in order to be able to do these same measurements. So we go ahead and we take and back probe onto CAN high and CAN low here, and we have 60 ohms. It's a good sign. Our terminating resistors are intact, and the system should, on that front, should be a go, okay? This is a slide that I got from Dave, and it's if there's going to be one slide that you take a picture of, probably should be this one, because this is going to be just simple voltage measurements that you take on the J1939 network or CAN network, whatever, and interpreting what you see for voltages. So very, very handy. Won't spend a whole lot of time on it kind of thing, but you guys can see that it's giving you an idea of what happens if CAN negative is shorted to ground, or CAN low, I should say, is shorted to ground. And this is what you'll see for voltage between ground and the pin 6, for instance, on your breakout box. If you're seeing this, you know the network is alive and responding. Then here's some ideas to help you along with your diagnostic journey, if you will. Here we are with a meter analysis again. Buses should not read 0 volts unless they're completely at rest, right? They will go to 0. It will go to 0 if the vehicle's been left long enough, right?
That's been my experience, yeah.
Right. Okay. However, once it's woken up and shaking itself, shaking the sleep off or whatever, 2.5 volts, okay, is going to be a good number, right, on both pin 6 and pin 14. But if you see an ongoing 0 volts, short to ground is probable. If you see a steady battery voltage, you've got a short to power. And if the network is talking active, you should see a fluctuation in your readings on here on this meter. I was in an AC Delco class just not too long ago, and the instructor recommended putting it in the AC volts range when you're doing that test. And I think his reasoning was that it was more responsive to the changing the digital stuff that's going on, the on-off.
Yeah, and you said that in the first session, Tony, and I thought about it, and you text me, and I said I've never tried it. I probably hadn't forgotten over the years, but it makes sense after seeing your really good Pico analysis by what's his
Adam
name?
Robertson.
Adam
Adam,
Robertson. You
yeah.
guys will see that in a few slides. And you look at that, and I've looked at the scope patterns. I agree. I mean, it's more of AC. Think about it. It goes above 2.5. It goes below 2.5. So it goes positive and negative direction, and that's alternating current. I mean, it's not a wall socket with 120, 60 hertz, like you might think of classical or a wheel speed sensor from a way back, but it is still an alternating low voltage, low current, and it makes sense you would see that if the bus was active.
Yeah, and I guess his main point was is that the meter is going to give you better information in AC volts as opposed to
Yep.
DC volts.
Yep.
So I thought that was a good tip for what
Yep.
it's worth. So, okay, you suspect you have a module, and I believe this came from Scott Manna. You have a module that has an internal short to ground. Well, that module, you isolate the module, disconnect the module, and go from with the ohm meter from the CAN bus terminals to ground. And if you see a low resistance going on, we're talking about probably 5 ohms or less, you have an internal short to ground on that module. So this is stuff that doesn't require any fancy equipment, right? I mean, this is pretty grassroots. It's what it is. The law of halves. I was joking with Dave earlier. I said Dave is a have and I'm a have not. And that's not what we're talking about here. This
You're the
is the
one that
law of
worked
halves.
at a
Yeah.
gold mine.
Yeah, yeah. I almost wish I was there now with the price of gold. But anyway, so yeah, the law of halves. So what is this? It's a simple diagnostic strategy where here you have a short across can high and can low here. And when you take a measurement of the resistance across pins 6 and 14 on your breakout box, you're going to see what should be probably less than 5 ohms, right? Is what you're going to see. And you know right then, okay, our termination resistor is being bypassed. We've got us a short across the network, right? So then you say to yourself, okay, so where do all these wires run and how am I going to narrow down where the problem is? Well, you're going to find a splice pack or someplace where you can disconnect the network, as you see here. And at that point, what resistance are you going to see with the measurement that you're taking? And that measurement should be 120 ohms. So you see right away, if we go back, right, with the network not being played with or not being disconnected right at the halfway point, you've got less than 5 ohms. So we've got that short taking place across those two, across the backbone in this case. And if we disconnect it and suddenly now we go to 120 and we're seeing that right hand terminating resistor, we know that somewhere on the other side of it is where that short is taking place. Now, you could further narrow it down, reconnect here, and then disconnect, say, here, and then see that the problem hasn't changed. Then or pardon me, the reading hasn't changed. Then you know that somewhere between there and there is where your problem is, right? So basically, it's continue, like cut the circuit in half, take a measurement, get an idea if your problem is on this side or if it's on that side. And then if you go in that direction, cut it in half again and look for a change. So that's the law of halves is what it is. And you can use it in lots of different areas kind of thing. Okay. Here we have a short to ground in the body control module. And if we take a resistance measurement between pin C, which is data high, and we go to chassis ground with the other probe, we're going to see probably less than 5 ohms. So it tells us right away our data high line is shorted to ground. So what do we do next? Well, if we suspect that it could be our body control module, we may have done it on some of these other modules, but we suspect it could be the body control module because that's where we've been getting these codes and all the rest of it. Disconnect it. And what should you see now with that resistance measurement? Should be above 2K, right? At this point. Again, we're measuring between pin 6 and ground, right? So this is probably, guess what? This is not a hard and fast number. but clearly we've made a change. We were measuring less than 5 ohms here. We disconnected the body control module, and now we're seeing 2 kiloohms. We know there's something going on with that body control module. And so that is where we go looking, obviously, and probably verify by measuring resistance across the CAN pins and the ground on that body control module before we condemn it. Don't forget wake up signals. So if you have a module that's not responding, or maybe a group of modules, understand that they may be waking, or pardon me, they may be looking for a wake up signal, and it may not be getting to them. Dave, you had an analogy on that, didn't you? I'm trying to remember.
Well, I just know that I've seen actually a spike when I've looked with a scope at a breakout box of CAN on passenger car light duty trucks. And then also sometimes instead of a spike actually on the bus to wake up, and there's sometimes a separate signal to do that, separate circuit. There's also sometimes just ignition on to the module. So piece of equipment, the truck, the car, whatever, turn the key on and the modules wake up and they begin communicating. So it
Right.
varies. And I'm guessing with all the diversity within J1939, my gosh. I mean, all those different pieces of equipment you named, one of those slides earlier, Tony. Good
Right.
grief. I mean, it's everything except the lawnmower in my shed.
Yeah, and keep in mind too, like with off-road machines, like mine equipment, you always have a master switch on those things. So
Okay.
and during normal operation, right, you'll have an operator who will take the truck and he will park it. And one of the last things he'll do as he steps down from the truck is he'll turn off the master switch. So that in turn, right, if you had, the whole business of having adaptives and all the rest of that kind of thing, okay, well, you're going to have some non-volatile memory in there to handle all that, obviously. Um, but anyhow, I guess the main point here is understanding the strategy,
Yeah.
okay, on your machine, and if and know to go looking for this and ruling it out as a possible contributor to your issue. Okay. We've shown you guys this picture before using a DSO for CAN stuff. And again, we don't have enough time to get into this in any real depth at all. My main point of showing you this is that to get started in this, you don't have to spend a buttload of money. This Pico, by the way, the software you need for this particular Pico scope is what they call the T&M measurement, or pardon me, the T&M software. It's not the automotive software, test and measurement software. It's all free. But you use the test and measurement software on your laptop when you're using the Picoscope 2204A module here. And this could be a way of not spending a bunch of money and getting used to the idea of using a DSO for diagnostics, because you will use it potentially for a whole lot more than just canned stuff, right? I
Yeah.
mean,
Yeah.
lots of stuff. So it's worthwhile messing with. Have somebody buy it for you for Christmas. Come on. I mean, you don't have any excuses, right? You know,
Alternator ripple.
that's right. On.
Yeah.
And the main reason I'm showing you this is from a guy I know named Adam Robertson, based out of California. He's a Picoscope uh, dude. And anyway, what he did here was he just created a known good waveform, and he put all of his callouts on it. So basically, he's just describing here what these data packets mean. This is again is outside the scope of the 1 hour that we had to do, today for J1939. But the main point is that once you get used to the idea of looking at this stuff and knowing what known good looks like, it's going to help you a whole lot more with figuring out where bad stuff is taking place, and just going to make you a better diagnostician. So it really all starts with known good. If you got the known good down, just like counterfeit money, we were just talking about that last hour, right? How do you know what bad money is? Well, you got to know what good money is first, right? And then you can sniff out the bad stuff really easily. Last point. When you're repairing CAN bus wiring, follow the OEM procedures. Get into the manual and find out exactly how they want you to do this. Because there's going to be some that say solder is okay. There's going to be some that say do not solder this thing. Getting your twist per inch right, or pardon me, your twist per foot right. Uh, if there's a specification for how far the twist has to go before it reaches the connector, same gauge, same length of wire, on and on and on. It's not to be taken lightly. You don't just go in there with a Scotch lock or a doggone crimp connector and let her have it kind of thing, right? I mean, you need to get this right or you're going to have ongoing problems. So just make sure to find out how the manufacturer wants you to deal with it. So again, we're just a little bit over time, but I don't know if we have any questions at all. If you have them.
I'm looking right now, Tony, and it looks like we've got answers pretty much. A question from Harley about that adapter. And Harley, I've got it up right now on Amazon. I bought a lot of stuff on Amazon if I don't have the patience to get it from my friends at AES Wave out in Fresno, California. Just, little stuff. It's at my house usually the next day or two. But this Autel, if you just Google and put in Amazon in there, it's 20 bucks, 1999, J1939 male to 16 pin OBD2 female. And it's just like Tony was showing. Plug that dude into the truck, 2014 and newer, right, Tony?
No, that's backwards compatible. That'll go back to the old 6 pins as well. Or
Okay,
not,
all right.
not the, pardon me.
But
Wait,
just for a breakout
not
box, yeah,
six
it wouldn't
pins.
hurt anything. Yeah.
But
So
it'll
plug
cover
it in.
all the 9
Yeah,
pins. It'll
yeah,
cover all the 9 pins.
yeah, plug it into that DIN connector, and now you got something that looks like a car, or like you'd have on a Volvo, or you said a Mac.
Volvo Mac.
Yeah,
They're the same thing.
yep. And then you can actually look at the wiring on the breakout box if you've got one of those in your shop, anyways, because you do not only the big rigs but the small stuff as well. So thank everybody. I appreciate every one of you for logging in, spending an hour with Delphi. I'm Dave Hobbs. Have been there forever, and we are really blessed to have heavy duty truck guys like Tony Martin and light duty diesel truck gurus like Tony Salas. We got two Tonys that are diesel dudes, and a host of other folks that are just good, not beyond good, experts at what they're good at. Got a lot of specialists out there in our contracting area. If you want a class at your location and you can get 15, 20 techs together, we can do it through one of our parts customers, or we can do it directly to you folks now. Got a guy in New Jersey with a nice shop and a little training center kind of in the basement of a house between the two buildings of his shop. And he's inviting other shops to come in and gets 15, 20 technicians, and we just directly go that way. So we could probably get a class where you are for 4 hours or whatever, or even a all day with hands-on. So we think outside the box, and we have a lot of boxes with our part name on it. I hope you support that as well. Tony, thank you. You did a great job. And there's Tony's email. So I mentioned to one of the, maybe Harley, is there a handout? Send an email to Tony, Tony Martin at gmail.com. Then he'll have your email. And if you're nice to him, he can then make a PDF of that presentation. And don't copy it and put it on the web. Just to be a courteous. But the PDF is pretty harmless, so he can email you the PDF. I'm sure it's not that big a file, and you'll have the handout if that was good. We do not have a recording of these. That might be something we're going to do when we start doing like 2 hour and 4 hour versions of these in the future. But right now, for an hour, we're just glad to have you for that period of time. Thank you all, and Tony, I'll let you wind it out with your final.
Well, if you have any complaints or negative responses that you want to share, dahobbs@finia.com is the correct email for that.
I was asking for that, wasn't I? Yeah.
Yes, you were. Anyway, yeah. So, yeah, thanks. I sure appreciate you guys' time. Thanks for taking the time and sharing these moments together, if you will. And we'll look forward to seeing you in future Tech Tip Thursdays.
Have a good afternoon, everybody.
Yeah, take care.